Hello. Today I wanted to have, it's probably just going to be a short video on trying to fix a purchased nut. This is what you see in front of me here is an assembly I've come up with for the auger boring machine project, and it's to support the pipe that runs along the skid on the auger boring machine. There's actually the blue is the pipe. This is the assembly that'll hold it, and then there's a mirror image of it over on this side. Unfortunately, my whiteboard is full of other details I don't want to erase, so I've only shown half of it. But anyways, these two pads sit at 45 degrees like this, and the pipe, so it acts almost like a V-block. And then this piece is a 2.5 inch diameter Acme rod, threaded, and this is an Acme nut. And then this is a hex. You can put a large wrench on here and turn it, and you can move this out and in to adjust the pipe once you have it in, and then also to move it in a more coarse way to adjust for different sizes of pipes. The basic idea, the design, is that there's just a frame here, and then there's a nut, and I need some support outboard of the nut because there's going to be a lot of force coming out of the board from the weight of the pipe. The pipe itself with the augers and dirt in it could weigh 8,000–9,000 pounds. So you're looking at, say, 4,000 pounds on each one of these supports. And you know, you could have hundreds or even maybe in the low thousands of pounds of force coming out with the friction of the pipe sliding along this support. So this Acme rod needs more support than just what this nut can give it. So my plan was to machine a part like this, a round piece, and have it neck down and be just a close sliding fit over the major diameter of the thread, and therefore it'll pass through the nut and that'll allow it to advance or retract. But this going on the OD of the thread will give it some more support and just stabilize the assembly so it's not rocking back and forth. It turned out I was able to buy Acme rod for probably just about the same price it would have cost me to buy the raw material if I was to make it myself. And I got nuts as well, so I didn't have to make the nuts. One of the things I have to do is the nuts are hex nuts, and in this situation I want to machine the hex off and just make it round. To do this assembly, what I want to do is make this piece with the whole undersize, then weld it on, and then set up in the lathe so that the pitch diameter, the axis of the thread itself, is running true, and then bore this out to size so that they're concentric. And then this is the problem I ran into is this is one of the Acme nuts, and the manufacturer of this nut made essentially no attempt whatsoever to relate the axis formed by the pitch diameter of the thread to any of the other features on this nut. So the hex itself tapers somewhat. It's not really noticeable by eye, but if you measure it, calipers, you can see. The faces run out. If you were to mount this on a threaded rod so that it's actually running on the threads, you see the sides of the nut just wobble, and not even necessarily together. Like, they're out relative to each other, they're out relative to the thread. There's not a surface on here, not even the minor diameter of the thread isn't necessarily concentric to the pitch diameter. I think when they make these, they form them and then they grit blast them, and they get this sort of dull gray finish. And then however they machine the threads, they put it in a machine and they machine them. And if you look at the minor diameter of the threads, it still has the grit blasted appearance. So it's just whatever was there when the thing was first formed, and it doesn't even run concentric to the pitch diameter, so you can't even chuck up on the inside on the minor diameter to hold it. So I needed to come up with a way to actually establish some features on this nut that would be concentric to the axis of the pitch diameter, and that was sort of the purpose of this video. I wanted to just show what I came up with. I've put a nut on this lead screw, and the lead screw is running pretty true, within a few thou, and just thought I'd show you some of the run out on the face of the nut. We're at least 25 or more thou run out on that side. Same thing on the other side. 25, just about 30 thou run out on the face. As I mentioned earlier, the minor diameter in the thread isn't concentric with the pitch diameter. The hex isn't related to the pitch diameter at all. Everything on the nut is out. This was my first attempt at trying to get, at least trying to get the nuts to run on their pitch diameter by pushing them up against the thread flank of the outside of the threaded rod, sorry. But as you can see, at the top, the nuts are kind of touching, but at the bottom they aren't. There's a gap there. And then what happens is when you tighten these against each other, the force is up here, so this nut goes that way and this nut goes that way, and they don't actually load equally on the thread flanks all the way around. I tried different combinations, flipping the nuts around, backing them against each other, hoping at least one, I could maybe get one combination where they'd be flat. None of them would sit flat on each other. So I thought for a while, I wasn't sure what I was going to do, and I came up with the following idea. Now, in order to get this nut to ride up on the flanks of the threaded rod and hold itself essentially square to the axis of the pitch diameter of the rod, you need, this nut's loose, it's got some play, not a lot, but it's got some. You need to find a way to load this nut so that it's being pushed evenly all around and not being pushed just in one corner. And the technique I came up with was sort of like an equalizer bar. Put a bar across and then push it with a tailstock. And what I did was, so the point wasn't just pushing on the bar, I'm gonna put a nut on here and push on it like that, and then this can pivot around to whatever it needs to. This is an idea I got from David Wilkes from his excellent site. He uses this often because he turns from chuck to tailstock, and when he has big pieces in the chuck and he's turning, he just likes to support it with a setup like this so that the piece doesn't walk out of the chuck. And it's actually a good way of supporting things like this because it allows it to go off at an angle, and it doesn't load the extreme point of the center where it might get damaged. And that's the setup. I couldn't show myself doing it because I need two hands. I don't have a stand for my camera, so I had to put the camera down. But you can see it's not perfect because it's only pushing in the two places, but it's very close to loading that nut up evenly all around so that it has a chance to load up on the thread flanks without being pushed off to one side. What it does, however, is it makes it so you can't machine the end of the nut. Obviously the bar is in the way. So then what you do is you come in and you machine this face of the nut using this tool, and it gets pretty close to the thread. I don't want to hit the thread on the threaded rod. What you do is you just go in with the tool with it not turning, and you touch on there, and then just back out about 10 thou and zero your readouts, and then you know to stop when you hit zero on your readouts. In this view, you can see the wobble is pretty apparent, and that's what we're going to machine away. I've taken about a 15 thou depth of cut, pretty light depth of cut. I don't want to put too much load on this, as the nut, its resistance to the torque of cutting is simply the friction applied by the tailstock, by the force applied by the tailstock, causing friction between the thread flanks and the nut. So I really don't want to take a heavy cut and have the nut jam. If the nut does jam, it's going to want to start walking down the thread, and then it's really going to dig in. So I just need to be careful with the size of cuts. Anything you do besides light cuts, keep your foot on the brake. Now you can see that part of the nut didn't clean up, and that part did, so we need to take another pass. And if you want to get an idea how much more of a pass you need to clean up, after you've taken an initial pass and the parts that didn't clean up are very easy to see, chances are the deepest part of this area not cleaning up is in the middle, between the 2 points where it did clean up. So what you can do is you can rotate that until your tool is pretty much in the middle. Move the carriage over until it just touches. And then look at the readout. Now, what I didn't show you before was when I started the cut, I zeroed the readout. I originally took a 15 thou deep cut, and then I zeroed the readout. Now, I see that I've been able to move the carriage a further 16 thou in pretty much the middle of the area that didn't clean up. So that tells you that I need to take at least 16 thou for this to clean up. So probably what I'll do is I'll take another, say, 15 thou cut, and then I'll take a 5 for a finish. Roughly. Blade in gear. pounding as there's a couple of letter B's stamped in the end of the space. And that's what that pounding is. It makes an interrupted cut. There's those B's. And you can see here there's just a little bit that didn't clean up. So I'll take a 5 thou finishing pass and that should clean up. And then we'll have a flat surface all the way around. And there, that's after the finishing pass. So now we've got a flat, cleaned up surface all the way around. And then I will set the other nut up and do that. And then I will show you how I do the opposite faces of the nuts. There, so now I have 2 nuts where the surface has been faced and it's good. It's square to the axis and we can tell it's good because it says so right on there. Now what I'll do is, instead of using the same technique to machine the back side, now that I have 2 good surfaces, I'm going to put them on the threaded rod and back them against each other, and then I can machine each end. So this is the setup to face the other 2 sides of both nuts. These are the 2 good surfaces backed against each other. There actually still is a very small amount of light. I'm not sure if it's going to show up very well or not. So they're not perfect, but they are a lot better than the original as received nuts. And actually, I'm filming these a little bit out of order. This is the second set of nuts I've done, and the first set of nuts I didn't get any light between them, so those must have went a little bit better than these. But regardless, it's enough of an improvement for the job I have to do here, and it's definitely improved them over as received. So just kind of the same thing. I'll take lighter cuts. Same issue, if the nuts jam, they're going to walk back this way towards the tool. Having thought about this since I did it, probably the safest way to have done this would have been to just take a normal right-hand turning tool. This is a left hand. Take a right-hand turning tool, turn it upside down, run the lathe in reverse, and feed in. And in that way, if the nut was to jam, the nut would want to walk away from the cutting tool instead of walking into the cutting tool. But I'll just take light cuts and it should be fine. So this part's no different than what I did before. It's just a similar light facing cut with a foot on the brake. That's just more of the same. I'll let that finish off. That end is finished. And then now to do this end, you just use a regular right-hand turning tool and just feed across the same way, just as before. A couple of passes and then a finishing pass, and that end will be done. And then that's both sides of both nuts are square, flat. There, that side is completed. So that's 4 nuts now have been faced on both sides. 2 of them are going to stay as hex nuts, and they're going to end up being parted off to make jam nuts, and that is part of this assembly. But 2 of them I'm going to machine the hex away and make the outside round. and that's for the ones that are welded onto the part that then has to be bored out. One of the things I had to do at the start of the project, the first thing I did was I machined these threaded rods, just the ends for the various fittings that go on. And one thing I had to do, this is as much as I could get the rod in. It won't go through the spindle of my lathe. It just gets into the chuck and stops. So, you know, you have to have a bunch of overhang. And I wanted to check what the runout was out here before I machined these ends on. And I thought I'd just show you how I check the runout of a Acme thread. This is a problem I had yesterday when I was trying to dial this threaded rod in before I machined the end. How do you dial in that OD when it's always moving out from underneath the indicator? And I'm sure guys I'm not the first guy to do this by any means, but it's the first time I saw it done. I came up with it yesterday on my own, and it's simply to engage the lead screw. And I know that this threaded rod is 4 threads per inch. I set my lead screw up to thread 4 threads per inch, and then I set the stylus on the top of the thread where I want to dial, and then just engage the half nuts and let it turn. Now it obviously wanders to the left and gets out of the range where you want to dial in, but for a couple of revolutions anyways, it's pretty close to where you want to dial in. If you watch closely, you'll see the slack in the feed gear train when I reverse the direction of the spindle. Watch how the stylus moves off the center of the major diameter. Fortunately, it's tight enough that it doesn't fall right off, but all you have to do is do your runout check in the same direction every time, and it'll always be in the same spot. Anyways, we can see the runout is a little over 2.5 hours, so, and that's acceptable for this job, so that's good. This is the setup for removing the hex, and I've just taken a few passes already just to try it out. Essentially just hold the threaded rod between centers so it's running true and it's stiff. Screw this nut up against the jaws, and then screw this one up against there. I don't have a wrench right now that's big enough for this, so what I've used are just some C-clamps, clamp them on like that, and use those like a wrench. And I can get it tight enough that I'm able to take these cuts. I'll probably just take light cuts anyways, so nothing moves. But you can see now my faces are running true. Both nuts are tightened against each other, so they've centered themselves on the pitch diameter of the threaded rod. So it should be concentric. The thread and the nut should be running concentric to the thread on the threaded rod. And now I'll turn the outside, and then the outside should be concentric to the threaded rod, which is ultimately what I'm trying to do, so that I can bore out the piece that's welded onto here and have it be concentric to the outside diameter of the threaded rod, as I mentioned at the beginning.
remove the hex, and the OD now running concentric to the axis of the pitch diameter, and the ends are perpendicular to that axis. And now I have 3 surfaces on this nut that correspond to the threads that are cut through it, and that'll allow me to accurately place the piece that will be welded on here. So that's the technique. I don't know if it's perfect. It's definitely a hell of a lot better than how the nuts were, and it'll be accurate enough for this job. Thanks for watching.